Thank you very much, Wolfgang, also for inviting me. It's not the first time I'm here. I've been here before, and therefore some of you will have heard part of what I'm going to say, but I hope you will survive anyhow. As you can see here, it is again the sun and solar activity that is at the center of attention. It's actually about 20 years ago that I started this work that I'm going to present here today, and when I started that work I had no idea that I would continue to work on it and still be talking about it nearly 20 years later. The outline of my talk is I will say something about solar activity and climate. In particularly, why should we care about cosmic rays and solar activity? I will show you some empirical evidence that makes it clear that there is a connection and there's something we need to understand. Just like Willy Soon was talking about, there is a real problem that needs to be understood. The main character in this plot in my talk here is cosmic rays and clouds. So I will show you some experimental results that indicate that we have a mechanism connecting clouds and cosmic rays. And then I will end up by showing you observations which I think are quite important, and I will explain why. So what are cosmic rays? Well, cosmic rays are mainly particles that are accelerated in stellar processes. It's mainly when a star explodes, a supernova, you get an acceleration of particles, and that means that space in itself is radioactive. You have particles moving at extremely high energy, and they shower the whole solar system with these very energetic particles. And solar activity, when these particles come, because of the magnetic activity of the sun, it can actually modulate the amount of cosmic rays that reaches into the Earth's atmosphere. Now, what I'm not going to talk about is that over very long time scales, the change in cosmic rays can be several 100%, but then we are talking many, many millions of years. But we're going to talk today merely about solar activity. So why is solar activity important with respect to cosmic rays? What you see here is a region of the heliosphere. You're supposed to have the sun in the center, and in this blue part here you would have all the planets. And all of this is actually the sun's, we call it the heliosphere, but it's really the part of space that is affected directly by the solar activity. The reason that it looks as if it's streaming downward, it's because the solar system is actually moving through interstellar space. So it's sort of like a downwind here. And cosmic rays try to enter, and you also notice that that this region here is going, it expands and contracts, and that is the 11-year cycle that you see here. And this 11-year cycle, it modulates particles that try to enter into the solar system. So what happens when the particles enters the atmosphere? What you see here is a proton that comes in with an energy of the order of maybe 100 giga electron volts, and it hits the atoms of the atmosphere at about 12 kilometers, and then you get this shower structure. And I will talk a little bit more about the shower structure in a short while. But the processes are so energetic that you produce new isotopes. For instance, carbon-14 is produced because of cosmic rays. And actually all cosmogenic isotopes are produced by this process. And this is important because carbon-14 we can use to reconstruct solar activity back in time. The half-life of carbon-14 is on the order of 5,000 years. And it means that we can actually reconstruct by using 3 rings solar activity back more than 10,000 years. So that was the introduction of cosmic rays. They are entering into our atmosphere all the time. We are penetrated by them all the time. But now we turn to the question, why should it be relevant for climate? And here you see one of these reconstructions of climate. And let me say just a few words about what kind of reconstruction it is, because this is the last 12,000 years. This is present, and this is 12,000 before our time. And we of course don't have any real measurements of temperature, but this is an indirect measure where you actually look at the number of icebergs that have moved over the North Atlantic. Because in the ice you have part of, for instance, Greenland, you have small stones, and as it moves over the North Atlantic, it melts and the small stones fall down on the bottom. And when they are in the bottom, you can take up the core and you can see how many small stones there are as a function of time. And that says how many icebergs that moves over the North Atlantic. And the interesting part here is this black curve going back. You see that there has been many oscillations in the ice rafting, that is the number of icebergs moving over the North Atlantic. But if you compare it with the carbon-14, you see a very nice correlation over this period of time. And this is just one example on this time scale. There are many, many examples that all indicate that there seems to be a connection between changes in solar activity, because these changes that we see here in the carbon-14 is caused by solar activity. So it looks as if climate is responding. Now the first variation here, this is actually the Little Ice Age, and here you had the medieval warm period, but you actually see that you have had many cold spells and many small what you call ice ages or warm spells. So you have had these oscillations over most of the last 10,000 years. So if we move to the Little Ice Age, here you see a picture. I mean, it's famous because you had all these pictures with the severe winters that you had in the Little Ice Age, and you see people skating and having fun. In reality, the Little Ice Age was not that much fun. If you make a reconstruction of temperatures, and we can say that we are moving closer to our time, so here you have the modern period with a certain data set. What data set it is, I'm not sure. But you see here the reconstruction where you see the medieval warm period 1,000 years ago, and then you have this period that after about 1300 you start getting a colder climate. Now, if you look down here, you see a reconstruction of cosmic rays or solar activity. And you can see that the changes are more or less identical or very similar to what you see with respect to the temperatures over this period. Now, at that time, around 1300, it was very bad for harvest. People started having problems. The crops, you had failure, and these continued failures actually meant that that at that time people were trying to understand why were bad weather happening all the time. Why did the crop go wrong? And authority at that time thought that the reason was witchcraft. And the most common, the most common thing that they thought sorcery was doing, that was actually bad weather. And so over this period here, I mean, more than 200,000 people were burned at the stakes. Many of them because of, most of them women, and many of them related to sorcery and bad weather. So it's, I mean, it was really a quite dramatic period. So you couldn't say that it was a CO2, but you had another explanation and you did something about it. Okay, so I showed you some correlations that indicated there seems to be a relation between solar activity and climate, but it doesn't say, you know, how strong is this interaction, how large is the effect. We can actually quantify it, and here's one example. This is actually from sea level, the sea level rate change since 1920, and you can actually see the solar cycle variation. The linear trend is taken out of this, and you see that there are these oscillations, and these oscillations that has to do with the heat that it goes into the oceans. And since you know the heat capacity of the ocean, and you can actually then calculate how much energy goes in and out of the ocean. And it turns out, if you do that, you get a result, which you can see here from the tide gauge, that over an 11-year cycle, it's about 1.5 watt per square meter. This is actually quite a large effect. Now, if you use the heat content of the oceans, you get a similar result, so it's a different data set. If you use the sea surface temperatures, you get a similar result. Or if you use the latest satellite data or observations of sea levels, they all give you a change on the order of 1 to 1.5 watt per square meter. This is actually quite large. And it is interesting that if you look at solar irradiance, at least as it is here, it is too small to directly explain these variations. So therefore, I mean, the idea that I am proposing is that you need some kind of an amplification in order to explain why it is. And it's interesting that if you take just 1% change in cloud cover, it will give you something that is on the right order. So no matter what the actual mechanism is that is responsible for this link, the sun has actually a quite large effect on climate, and it has to be taken into account. So what was the idea? The idea was, I mean, what could the link be? And the idea is that it has to do with the Earth's cloud cover. You see that the clouds, they actually cool the Earth. The net effect is a cooling, and it's on the order between 20 and 30 watts per square meter. And if you have a systematic change in the clouds, it will change the temperature of the Earth. So that might be a very effective way of amplifying any solar activity. Okay? So originally, this is the old result, and this is really what started me, where you see here the change in the cosmic rays. This is the red curve. And then we did with the ISCIP data set, and we had some recalibration problems and so on, or some calibration problems with the data set. But nonetheless, we saw a very nice correlation. So there was an indication that perhaps cosmic rays are affecting the Earth's cloud cover. That was the general idea, and that was sort of what we tried to pursue. Okay, so this opened up the question, if there is a link between cosmic rays and clouds, what can the mechanism be? Because what are cosmic rays doing so that it should change the Earth's cloudiness? And that was sort of the fundamental question that we asked a number of years ago. And in order to understand this, you have to think about how clouds actually are formed. And in order to form a cloud, you have to have a surface in the atmosphere that the water vapor can condense on. And this is what we call a cloud condensation nuclei. So water vapor can condense on these. I mean, these particles need to be in the atmosphere. But the fundamental question is then, where do these cloud condensation nuclei come from? And if you go over the oceans, you find out that a very large fraction of them is actually produced directly in the atmosphere. And they are simply produced by gases that somehow condenses and form very, very small clusters, about 3 nanometers. And then subsequently, in order to become a cloud condensation nuclei, they have to grow. And that is a process that takes several days, almost a week over the oceans, and then they can affect cloud properties. So the idea is simply the idea we had was that ions produced by cosmic rays, they help the process of nucleating new small clusters. So if we produce more of these small clusters because of change in the ionization from cosmic rays, then we would also produce more cloud condensation nuclei. If you change the cloud condensation nuclei, you change the clouds, so you change the radiative budget of the Earth. So that's the general idea. And to give you the very good example that if you make a systematic change of aerosols, then you change the cloud properties. What you see here is a part of the Pacific, and you see here these stripes. These are actually ships that have been sailing, and what happens is that the engines of the ships, they are pumping out aerosols. So you are producing many more aerosols along a track. So you have many more cloud condensation nuclei. So you condense on many more particles, and you get this white stripe. And you can imagine that the radiative properties are completely different along the white stripe. And the general idea is that if you can do this all over the ocean, if you can do this all over the Earth, then you will be able to change the energy budget of the Earth in a very subtle but firm way. So apart from having these observations, with these ideas, we can actually test them in the laboratory. And this is part of our laboratory in Copenhagen. What you see in the back here is a 2x2 chamber, 2x2 meters. It's a cube, so it's 8 cubic meters. And then we have all kinds of instruments on it. But what we do, we try to put in clean air, as clean as you have over the oceans. Then out here we have radioactive sources that can send in gamma rays on both sides, so we can increase the ionization. And when we do this type of experiments, and this is what we did in 2006, we got this result, which is sort of the fundamental result, because it shows that as soon as you increase the ionization, you keep everything else constant, then you actually increase the number of small nucleated particles. So ions do help the promotion of these small aerosols. So there is a mechanism producing new aerosols, and ions seems to be a close part of it. Now, this result was actually confirmed by the cloud experiment in CERN in 2011. So we can say that experiment says yes, if we have ionization, we produce more of these small clusters. But then there's a problem, because many people were saying to us when we got these results that, okay, you see it in your laboratory, but when you go into the real atmosphere, then you would not, then there are so many, when you go into the real atmosphere, there are so many processes that your process will just drown and it will not be important. But This was actually even confirmed more by modeling work, where you had used climate models with aerosol. I mean, that modeling aerosols also. So what they did was that they had a mechanism in the model, and they produced extra aerosols from cosmic rays. But even though they produced extra aerosols, they didn't grow to cloud condensation nuclei. So even though you produced more of these, you didn't get more of the cloud condensation nuclei. I mean, the increase you got is so small that it doesn't matter. So this is actually saying that the whole theory is dead, and it couldn't. I mean, it couldn't survive that. It was a good idea, but it didn't work. However, we actually did some experiments where we saw that as soon as we used ions, then all the small new particles actually grow to cloud condensation nuclei. However, if we just added extra aerosols or small aerosols, then we saw the effect that they didn't grow up to cloud condensation nuclei. So experimentally, we actually shown that ions are important. Now, the rest of the talk, I will try to convince you that if you look at observations, you can actually see these effects very clearly. So the idea is that with respect to observations, here you see the sun, but you actually don't see the direct light from the sun. You see just this activity that you have, where you have what we call coronal mass ejections. It's with some plasma that is thrown out into space, and it might hit the Earth, and that might be important because it changes the cosmic rays over a very short period of time. So I'm going to talk about a special event which happened in October 2003. So here you have the sun, here you have the Earth, and you have the heliosphere, and you have the plasma streaming out. And you see you have these explosions that happens, and then they move out. This is these coronal mass ejections. And because they contain also magnetic fields, they screen against cosmic rays. And here you see what happened to the cosmic rays as you measure them. So here you have a certain reference level, and then this explosion from the sun is passing close by the Earth, and it makes a big drop in the cosmic rays over a few days, and then within a week or two, it slowly recovers. So this is a very strong event that happened in October 2003, and it's measured in a particular neutron monitor. And this is an important point, because the neutron monitor, it has a certain count. I mean, here you have a count number of 3,800, and the number of count depends on where the station is located, because if it's located in the polar regions, then cosmic rays can much easier move down. That means the low energy can come in because the Earth's magnetic field is weak. Whereas if you go to the equator, where the magnetic field is strong, then much fewer cosmic rays of the low energy can come in. So therefore, the response that you get in a neutron monitor depends on the energy. So what I really want to do is to figure out how is the ionization changing during these events. And if I know how the ionization is changing, then I can compare it with what is happening to clouds over the same period. Okay? So what we do is that we can actually take all stations that are operational. Here each cross is a station, and from that we can actually extend, we can get a decrease in a relative decrease in the cosmic rays depending on the energy that they are responding to. Up here you have muon detectors. These are not neutron detectors, But the whole point of this figure is just to show you that we can actually extract the cosmic ray spectrum, how it changes during these coronal mass ejections. So when we have how the spectrum is changing, that is how the energies of the cosmic rays are changing due to the solar activity, we can then use a model to calculate the ionization in the atmosphere, and this all to do with these showers that goes down through. You have a proton coming in, and then you get this cascade of secondary particles, and they are ionizing in the atmosphere. And I can then run this program for all kinds of energies and also from different angles, and I can make what we call a Monte Carlo simulation. And then when I know how the incoming cosmic rays are changing, I can use this to calculate the change in the ionization in the atmosphere. And here you see a very nice result. This is actually the height in the atmosphere. So this is 30 kilometers up in the atmosphere, and this is the surface. And this is the ion production. So the black curve here is actually solar minimum. This is like a reference level that I'm using. So what you see is that when you have these coronal mass ejections and they hit the Earth, then the ionization drops. And some of these curves here are dropping even below the red curve here. That is actually solar maximum. So over 11 years, it changes from here to here. But what you see is that the focus decreases, the coronal mass ejections, they can make changes in the cosmic rays which are on the same order as an 11-year cycle. It's just to say that this is a very strong event. So they are really probing the atmosphere with these events. So we did this work, part of this work we did in 2009, and it was published. And I've shown this before. And what you see here is the cosmic rays that are dipping. This is day 0. This is 15 days before, 20 days after the minimum in the cosmic rays. And you see that this is the AeroNet data, and AeroNet, it has to do with the aerosols. So now we are looking at what happens to the aerosols. And you actually see a very nice dip in the aerosols following the cosmic ray decrease. And then we used a number of different satellite data sets, and they all show the same. The cosmic rays are dipping, then you see an effect in the liquid water content of clouds over the oceans. You see here Moody's data, and you see here, this is the ISKIP data set. So you actually see a response in all of them. When we published this, then immediately a number of papers was published saying that they used different focus decreases than what we had used. And they showed that, they used maybe only one of the data sets, like the ISKIP data set, and they got the result that they couldn't see any effects. So in the IPCC report, it was reported as people don't actually see this effect. So it's probably not real, at least it's too uncertain to take seriously. So that was sort of the conclusion on this work. So I will now report to you some of the things that we have done. We are about to, these are the new results, and I'm only showing a little bit of what we have done. But let me give you the first hint. The first thing is that I want to show you that the effect we are seeing, we are only seeing in liquid clouds. So here you have combined cloud fraction from the Moody's data set, and what we are looking at are the 5 strongest focus decreases. And you see that there is a very clear dip in the cloud fraction here, and combined that means that it's both ice and liquid. So you see a dip, and you also see the significance of these, the statistical significance, and an enormous part of the work is actually to do the proper statistics in this case, so we avoid being attacked for that problem. But you see a very nice dip, but if you look at ice clouds, you actually don't get a significant result at all. But if you only look at liquid cloud fraction, you get the significance. So therefore we conclude the effect is mainly in liquid clouds that this is seeing. Now, in the Moody's data set, it's special because you can actually look at a large number of cloud parameters. And when we look at, for instance, the effective emissivity of clouds, we see a very nice dip and we have large significance. The optical thickness, liquid water paths, liquid cloud fraction that we just saw, or the effective radius. And there you actually see that the effective radius goes up, meaning that because you have fewer cloud condensation nuclei, then more water vapor will condense on it, and they are supposed to get bigger. The thing that we don't get a significant result on is cloud condensation nuclei. And that is actually expected because when we calculate from cloud physics the kind of result that we expect, we find out that the size of the signal that we expect in this parameter here is within the noise. So it's not surprising. With respect to the cloud condensation nuclei, we actually saw already that the AeroNet data gave a good result. So we already know that something is happening in these data. I can do the same thing with the ISKIP data set. If you look at all infrared clouds, you see a very, very large dip and a high significance. Then there are some problems with the, if you use infrared low clouds, you don't get a very good result. It's actually not significant. But the reason is that you have clouds on top of each other, and the satellite is only seeing the top clouds. And if you're looking for the low clouds, then the changes you see here can be because there are changes in the layers above. So that actually distorts everything. Okay, so one thing we did, and this is the last slide on this part, is to make a principal component where we use all the data set, the special sounder microwave imager and the ISKIP data set and the Moody's data. So it's about eight cloud parameters. And what this statistical method do is that it sort of looks for whether there's a common signal. And you see we get a very, very large signal here. And none of the 10,000 Monte Carlo simulations gave anything that was so large. So it's completely outside the noise of the system. So in summary of this part, there is a real response in clouds to cosmic ray decreases. And that is, we feel quite confident now that the signals are real. So this takes me to the last part. And this is just some comments about how things has evolved over the period that I've been involved in this. Just a few months ago, a new sunspot record was released, and the red one here is the old sunspot record. And the thing is that you can see that here that the adjustment is quite big, so you have a much higher sunspot number in this new adjusted data set. And the interesting part, of course, with respect to climate is that in this new data set, you get a flat line, more or less. So it doesn't look like it can explain 20th century warming at all. At least that was what you then heard from all media. So it says corrected sunspot history suggests climate change not due to natural solar trends. Solar activity is not linked to global warming, and so on. So this said more or less that now every solar theory is more or less dead, and the solar theory only lasted a few years before it died. But as a matter of fact, I mean, I could bring up many tombstones, because over the years, and I just looked mainly for BBC, I could see that they have actually said that it was dead many times. The sun, minor player in climate change, no sun linked to climate change. I can't remember. Sun's influence on modern day global warming may have been overestimated. Cosmic rays not causing climate change. So this is something that happens quite regularly. Now, with respect to the new sunspot record, I mean, I don't get it, but if you look at magnetic activity, I mean, if you, instead of looking at the sunspot record, but look at, for instance, magnetic activity. Now, this data here, that is actually the geomagnetic disturbance. That is, you have the Earth, and you have the magnetosphere, and if you have a small, you know, like a compass magnetic needle, then when the solar wind hits the magnetosphere, it makes small vibrations in the direction. And here you have sort of the size of these vibrations since 1850. And you can see that the intensity of these vibrations has actually increased over the 20th century. This is the inverted cosmic rays, actually. But if you look at cosmic rays, in the form of beryllium-10 data, then you have the exact same thing. It actually starts here. 1850 is here, right? So you see that there's a large decrease, which corresponds to an increase in the sun's activity. So it actually indicates that at least the magnetic activity has not been flat at all over this period of time. And then people have been saying that, I mean, okay, maybe these effects has to do with some climate effect on the measurements. I mean, if you look at beryllium-10, it has to do with precipitation in Greenland. And maybe the precipitation has changed due to climate, and therefore you have, I mean, that you have some climatic influences. So in some sense, it's not independent. However, if you, for instance, look at stone meteorites, they fall down on the Earth once in a while. And just like tree rings, where they have carbon-14 in them, stony meteorites are also exposed to cosmic rays, but they're exposed to cosmic rays outside the Earth. So they're moving around, and then something perturbs them, and they fall down. And you see here, people have collected these meteorites. Here is some of the first in 17-something. And you have different meteorites. But in the meteorites, they actually have you know, leftovers of the cosmic rays that they have been exposed to. And one of the isotopes is titanium-44. It has a half-life of 63 years. And if you then take these stony meteorites and measure the half-life of, or measure the amount of titanium in this, you can actually reconstruct how much cosmic rays they were exposed to. And you actually see that there was a little ice age where you had a much weaker solar activity. So the magnetic activity most definitely changed, and I don't understand how the sunspot record can be completely flat at the same time. So that's the end. I see that variations in cosmic rays, they seem to be associated with changes in Earth's climate. And there are so many examples that it's completely certain that changes in solar activity has an effect on climate. Now, the work that I'm doing, it seems to suggest that clouds are a key player and that cosmic rays are affecting the cloud. So what I showed you here was the last part, which I think is quite strong, is that we see the whole chain from solar activity to cosmic rays to the change in ionization to changes in aerosols, and then finally changes in cloud. So we have more or less the whole thing from observations, and I think, more effort should now go into understand exactly why aerosols are surviving better or worse depending on the ionization. Thank you.